Hello everyone. Today is the 56th day of Leetcode 75 challenge. Let's begin with the 56th question. Question 875, Koko eating bananas. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now, let's understand the problem in the easiest way possible. So, you are given an integer array, piles of length n, okay? And each element piles I or piles of I represents the number of bananas in ith pile, okay? So basically, you are given an array which is called as piles, and each pile has a value. Suppose this represents the number of bananas in that particular pile. Okay, Coco has h hours to eat all the bananas before the guard returns. Coco can choose an integer speed k, which represents the number of bananas she eats per hour. Okay, each hour she selects one pile and eats up to k bananas from that pile. If the pile has fewer than k bananas, she eats all of them and does not eat anything else that hour. Coco cannot eat more multiple piles in the same hour. Basically, if suppose k value is 3, which means that Coco can eat 3 bananas per hour. Okay, this is what the k means. So if Coco comes here, so in that particular hour, she will eat only this pile. Okay, suppose if she comes in the first pile and she tries to eat this pile of bananas, in 1 hour the maximum capacity she could eat is 3, right? But here we have the value 2, so there are 2 bananas in this pile, right? So she could only eat 2 bananas and she has to wait for that hour to be completed. Okay, she cannot jump in any other pile and eat one banana from it to make it 3 bananas per hour. Got it? And she, if the Coco comes and sits in this pile which has the value 6 or has 6 bananas, she will take literally or 2 hours to eat this 6 bananas in that particular pile. Okay, so our task is to find minimum integer k such that Coco can eat all the bananas in all pile within h hours. So we have to find a particular value of k, so that when that value of k or the number of hours taken in each pile adds up to equal to h. Okay, so I hope you understood the problem explanation. Now let's look at the constraints. The pile's length could be 1 to 10 to the power 4, and h value could be from pile's length to 10 to the power 9. Okay, and piles of I could be from 1 to 10 to the power 9. So I hope you understood the constraints also. Let's move to the next slide. Now let's understand the input output explanation. So let's take this example 3, 6, 7, 11, 11. Okay, here if I take k value as 11, that means she can eat 11 bananas per hour. Okay, so in 1 hour she will eat these bananas. It will take 1 hour, 1 hour, and 1 hour, right? So total taken 4 hours. But this is less than the h, which is 8, right? We have to find a value which sums up to 8. Okay, so let's take another value. Let's take 3. Okay, she says that I will eat 3 bananas per hour. So this will take 1 hour, this will take 2 hours, this will take how many hours? 3 hours. How many hours this will take? 11 divided by 3, 3 into 4. Basically, it's like 3 into 3 gives me 9, right? And the remainder is 2. So something point will come and you will write 3, 3, 6, and then it will be 18, right? So we have to take still value of this, which will be 4, correct? So total adds up to how much? 4 plus 3, which is 7. 7 plus 2, 9, plus 1 gives me 10. And now 10 is greater than the h, right? Which is 8. So we cannot take the minimum value also. Okay, so now let's take 4. Okay, if we take 4, then what happens? It will take 1 hour, it will take 2 hours, it will take 2 hours. How many hours will it take? It will take 3 hours, because 4 into 3 gives me 12, right? So we, if we add this up, how much is it? 3 plus 2, 5, 6, 7, 8, right? Which is equals to the h. Therefore, that is why the output here is 4. Okay, similarly here also the output is 30 because h is 5, which is equal to the size of the piles, okay, or the array. Therefore, we have to take the maximum value from this particular array. Like we have here, she has taken in the example, they have taken the maximum value from here, right? That is why in each hour they were able to complete the complete. She was able to eat all the bananas, right? So I hope you understood the input output explanation. Let's move to the next slide. Before going to the further slides, let's understand what is binary search or the concept of binary search. Fine. A binary search is an efficient algorithm that finds a target element or optimal value by repeatedly halving the search space. While commonly used on sorted arrays, it also applies to monotonic functions. Monotonic functions basically means, I will explain that. Okay, let me explain what is binary search. Binary search is basically, if this is a range, right? This is a range. So you keep on doing half of it. Suppose you started here, okay, in the middle, and then you will make the range half. Okay, then you have this particular range with you, then you again started in the middle, then you again make the range half, right? So this way the binary search goes. Okay, I will explain in more depth. So you could see here, it comes in monotonic functions, biotonic function sequences, and decision based problems with a clear true false boundary. So monotonic functions means increasing or decreasing, which basically means you have a sorted array in clearly increasing or strictly increasing manner. Fine. Or decreasing means that the number is strictly decreasing, 5 4 3 2 1, whatever, right? So that is a monotonic function. uh, that is a range in which you will use the binary search in a monotonic function. Okay, then comes the biotonic sequences. Biotonic sequences are basically the first it goes on increasing manner, then it goes on decreasing manner, and then it goes on increasing manner, right? Or it goes in vice versa way. It comes in decreasing, then it goes in increasing, this way. These are the sequences I have given you. Okay, and decision based problems with clear true false boundaries basically just it's way like you have a range and you got a value. Is it equals to the number which we are going to find or not? Then in that case we use this decision based problem. This is just a format of the sequence which you get, in which you can clearly figure out whether you have to use binary search or not. Okay, so it works wherever the solution space has a predictable pattern, enabling us to eliminate half of its at each step. Okay, it has to be a predictable pattern, right? Since monotonic stack is a predictable pattern, biotonic is a predictable pattern, right? So though that's the way it goes. Okay, now how binary search works, fine, that's the important thing. Suppose let's take a range. Okay, uh, 1 2 3 4 5 6. Okay, and start with the entire sorted array. So this is a sorted array, right? Now how it work? We calculate the midpoint. How to calculate the midpoint? 0 1 2 3 4 5, right? So what is the low value here? So we have two variables in binary search. One is low and one is high. Okay, and another is mid. Now low takes the uh, index value from the starting, and high takes the index value from the backside, and mid is the calculated value for the particular range mid index. Okay, so low is basically here 0 and high is right now is 5, right? And if we calculate this, how much it going to be? 5 divided by 2, you get 2, right? Okay, you get 2. So this is the mid value right now. Okay, so what happens? You got 2, right? So you come to index 2 here. What is the value of 2? It's 3. Fine, wait. Now thing is, we compare the mid with the target. Suppose basically we use binary search to find a target value. Okay, so the target value, suppose here is 4. Okay, but you are standing at 3, right? Because you got a mid value as 2. If you could see, if it is equal to the target found, if the target is less than the array of mid is mid is the index value, right? And here array of mid, which is array of 0 to array of 2, is the value is 3, correct? And but we were searching for 4 value. The target was to be 4. Okay, now you could see that, okay, the target value is greater than the mid value. Okay, so what you will do, you will search the right half. Now you will understand what is the repetitively halving the range. Now what will happen? Your low, so low value will come here. Okay, since high was standing here itself, because this is not the range you need, right? 3 is not required in your search space, because 3, because the value which we are finding is greater than this particular value, right? So we'll make the range here, right? So what will happen? Now low value is what? Low value is 3, high value is 5 right now. and mid value is 2, right? So now what happens? Now you will calculate this mid value again, right? 3 plus 5 gives us what? 8, right? 8 divided by 2 gives us 4. So the mid value for this range is this, right? You come here, fine. Now you will check that okay, this 5 is greater than the mid value, the target value, right? This array of mid is greater than this target value. Now what we'll do? We will go for the search the left half of the range, whatever you have, right? So what happens in that case? Since low was standing here and mid was here and high was in the end, right? Because this space is done, right? We don't require this space anymore, and anything beyond this space is not required also, right? So what will happen? Now L value is 3, right? So 3 plus 4 gives me what? Divided by 2 gives me 7 by 2 gives me 3, right? We get 3. So what will happen? The high will come here and it will stand here, okay? And mid value is 3, correct? Now what happens? You check, okay, you will see that okay, the mid value is 4 and the target value is also 4. Therefore we found the target. So we then return this particular index, or we return true or false as per the question, right? So we repeat until the target is found or search interval is empty. If the search space says that, you might not have the target, right? And if uh, H comes here and L comes here, because basically they cross each other, that means that the value is not present in the search space. Okay, so I hope you understood that how binary search works. Now binary search basically works on sorted array, ascending or descending, or biatonic arrays, as I said, or monotonic functions, right? So these are the ways where binary search happens. You have to look for a pattern there, okay? And why it's efficient? It's efficient because the best case is O of 1 if the middle element is the target, and average worst case is log n. Each step halves the search space. So whenever you do a half of any search space, suppose this is the search space, right? And if you iterate, it will take O of n time complexity. But if you make it a half, you came here and you make it a half, and again you make it a half. So this is a time. This is basically a mathematical calculation. When we do something, and any step, if we make the particular thing in half, 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 like a merge sort, time complexity comes out to be log n, right? So that is why it is much more efficient than any other iteration. And search complexity usually takes one time complexity, and if you are doing a binary search space, then it takes log n recursion stack. That's all. Now this binary search is basically efficient for fast lookup in sorted data, optimizing problems with monotonic pattern, reducing the brute force time from O of n to log n. Okay. Now, where binary search is used? Binary search is basically used in sorted arrays, basic direct applications like binary search question number. This I've just given you the references of the questions also and where it is used. Right there, this is what this particular PPT is. This slide is all about. So, like first and last occurrence, if you have to find the first and last index of target, right? They find the first and last position of element in the sorted array. These are the questions where you need it. You could go and practice these questions if you want, like search insert positions. If target not found, return the positions where it would be inserted. Example, search insert position. Basically you have to insert 7, right? And you got a value 5, you got a value 6 and then 8, right? So 7 will be inserted here, right? So this could be done using binary search. Finding pink element in an array. Peak element comes in the biatonic sequence, as I explained earlier, increasing and decreasing, right? So this is will be a peak element, right? Then you have to find the condition why it is a peak element, because the left hand values are lesser and the right hand values are greater than this particular element. Now rotated arrays are also there. Rotated arrays also work as a biatonic sequence. Suppose you had 4 here, 1 2 3, right? So it was a rotated array this way. Modified binary search to handle rotated version. This is question number, you could go and check in Leetcode 33. Koko eating bananas or minimum eating speed. This is the most common and most important question to understand binary search on answer or binary search on answer space, not the array. Answer space is basically you have to figure out by yourself that what could be the range of binary search rather than depending upon the array. Okay, like you have to assume that the search space will be n or it would be 6 or whatever depending upon the answer. Fine. So I hope you understood the binary search concepts. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's start by understanding the goal first. We are given an array piles where each element represents the number of bananas in each pile. Okay, in a pile. Coco can eat bananas at a speed of k bananas per hour, choosing only one pile per hour, right? So if the pile has fewer than k bananas, she eats them all and does nothing else in that hour. Okay, she needs to finish all these bananas at most h hours, not actually at most h hours. It has to be equals to h hours. Okay, the goal is to find the minimum value of k such that the Koko can eat all bananas within h hours or equals to h hours. Okay, so what could be the brute force solution? The brute force solution could be 3, 4, 8, 9, whatever it is. Let h be 6. Okay, so brute force could be you iterate over each of the piles. Okay, suppose you took 3. Okay, then you have taken 3. Now again, what you will do? You will divide this value by 3, right? So you will get 1. It will take 1 hour, right? Then again you will come here, you will divide 4 with 3. You will get 1 point something, so it will round up it to 2. Okay, you will take 8, you will divide it, it will be 3 hours. Similarly, it will be also 3 hours, correct? So time complexity to do this will take O of n into n, or you could say O of n square. Okay, and this will result in runtime error because it will cross the constraints which were given to us, which is basically 10 to the power 9. Okay, or you could say 10 to the power 4. So let's try to find the efficient solution for this. Let's visualize the process. Okay, let me take an example first. Okay, so let's take this example. Now here we know that minimum in 1 hour, how many bananas she could eat? She could eat one banana, right? Or the Koko could eat one banana. And how many maximum bananas Koko could eat? If you guess correctly, suppose here, if you remember one of our example, the h was equal to the length of the list itself, right? Which was, suppose here we have 4, right? Length is 4. So what will happen? She has to take that number of bananas so that in each hour she could eat everything, right? So for that, what you will do? Most basic thing, you will look for the maximum number of bananas in a pile, right? So here, if you see 11 has the maximum number of bananas in a pile. Eating this per hour, it will take 1. So it will also take 1 because it is less than 11. It will also take 1. It will also take 1. Therefore, in 4 hours, she will be able to complete, or the Koko will be able to complete eating all the bananas from the piles, right? Within the given h hours. Or you could also take value more than 11 also, but that will not make sense, right? Because we know that maximum number of bananas in a pile is 11. So at most she could take it will take 1 hour to eat 11 bananas, right? So taking more than 11 will not make any sense, but you could take that. But more logically, taking 11 will make sense. So what happens? Minimum number of bananas could be 1, will be 1, and maximum will be max of the piles, okay? Or 11 here, okay? One thing is sorted from here. Now you have figured that out, okay? I will write it here. Mean could be 1, would be 1, and max would be max of piles, okay? Or the array. Now how you will reduce n square to something lower time complexity? If you could see, we are asked to just find the value, find the k value, which could be anything, right? Between 1 to 11, right? Because if you remember the example, for this particular example, the output was 4. So that output would have been between this number line 1 to 11, correct? So from here we could figure out, okay, so there is a number line which is from 1 to 11. You need to find a value enclosed from 1 to 11, okay? Anything between that, including 1 and 11. And also the order of the solution does not matter. We just need to find the value, right? So but we want the minimum speed that still lets us finish in h hours, right? Trying every k from 1 to max pile works, but it is slow. Since total hour decreases as k increases, if you could see, also there is a logic. If you could see, if you take lower the value, suppose if you take 3 and if you divide it by the value here, or if you take the lower value, maximum time it will take, correct? And if you take the maximum value, it will take the lower time. That is a common sense, right? So if something comes to us and tells us about to reduce the time complexity from n square to something less, it could be n log n or n log n, right? So here log n is not possible, n is also not possible, right? Let's try going for log n. And for log n, what we could do, we could try using binary search here because it is a monotonic sequence. Okay, let me tell you why. Because we have a number line from 1 to 11, right, which is sorted, right? Since it is sorted, we could directly use binary search on it. Simple as that. That's all. Okay. Now let's see how we're gonna solve it. What you could do is that I will draw the number line here. 1, 2. So this is the number line. Okay. And we know how binary search works. Here L is 1 and H is 11, right? So when you find the mid value, it will be 12 divided by 2, which is 6. Correct? So you're standing at 6. Let me clear this up. So now M is 6 here, right? So what we will do? We'll come here in this particular array. We'll try to divide 3 by 6, 6 by 6, 7 by 6, and 11 by 6. For this, how much you will get? 1. For this, 1. For this, 2. For this, 2. It sums up to how much? 4, 5 plus 1, 6, right? Is 6 equals to h? It is not. It is not. So what we will do? So we have already discussed previously that if the dividend or the denominator is greater and we get a shorter hour, so we have to reduce that particular value. So we have reduced this 6, right? We have to reduce this value. Then not only we will get a value which might result in some greater total, greater sum. So it might be 7 or 8 or 11 or 9, whatever. Got it? So for that, what we will do? We will try to decrease the denominator. Okay, smaller the denominator, greater the output. Correct? Simple maths logic. So what will happen? We will reduce this 11 to 5. So our h becomes 5, right? Because it is mid minus 1. Now our range is this. Because you know that anything greater than 6 will reduce in smaller value, which will not be good for our answer. Okay. Now our range is 1 to 5. So 1 plus 5 divided by 2, it's 3, right? So our mid will become 3 now. So what we will do? Now we'll go back here and iterate the complete array. 3 divided by 3, 6 divided by 3, 7 divided by 3, 11 divided by 3. It's 1, it's 2, it's how much? It's 3, it is also 4. Okay, so it sums up to 7, 8, 9, 10, right? Greater than h. So we know that taking 3 is uh, increasing our hours. So we have to reduce our hours. That means to reduce the hours, the denominator has to be greater than 3. Okay, so your search space boils down to 4 to 5 because anything less than 3 will increase the hours. Okay, if you divide by 2 or whatever, 1, but anything greater than 3 and less than 6 might result in the specific hour which we required. So our range becomes 4 to 5. Okay, so what you do? 4 plus 5 divided by 2, it's 4. Correct? Now mid is 4. Again you go back to this particular array and you divide it. 3 divided by 4, 6 divided by 4, 7 divided by 4, 11 divided by 4. It is 1, it is 2, it is 2, it is 3. Sums up to how much? 8. Correct? Which is equals to h. So we figured out that 4 is the exact value or the exact number of banana seeds you did per hour so that it becomes equals to h. Okay, it's a pretty simple and easy problem, right? Let's move to the next slide. Now how we can simulate this? So to simulate this, what we could do, we can define a helper function, calculate total hours, piles comma k. This I will explain you why it is piles comma k. One thing is a binary search. First let me explain you this, which will have the low value is 1, h value will be the maximum of the piles. Okay, this becomes the eating space. Okay, while low is less than high, less than or equals to high, we calculate the mid value, we compute the total hours, which is basically the mid. Okay, how many bananas she gonna eat per hour? Okay, we get it from there. Now what we do, we pass this mid value to this particular function, calculate total hours. Here we have the piles array and this particular mid, which is k. Okay, so what happens, you iterate the complete piles. Okay, and you have a variable total here in which you keep on adding the math. That simple as that. What you do is that piles of I divided by k, which is mid. Okay, and you take the seal value of it, not the floor value, seal value of it. Because if suppose we divide 2 by 8, so it will be just 0, 8 0 into by 0 gives me 2, right? But even if the value is less than the k, we have to stand there, right? And it will take at least 1 hour. So that is why this 0 value is something 0 point something something, right? So seal value for this will become 1, right? Simple mathematics. So here we will calculate the total hours taken, and then we will return this function, and we will check the total hours which we got, okay, from this particular function. If it is less than or equals to the given h, what do you do? If you remember, high, mid minus 1, correct? If it is less than, that means we need a shorter denominator, okay? And if it is greater, therefore we need a bigger denominator. That's why it becomes mid plus 1, okay? At the end of the loop, low will be pointing to the minimum valid k speed, okay? What we figured out? We figured out that the relation between speed k, the time, is inverse and monotonic, which makes binary search applicable. We avoid checking all the values of k, instead use a logarithmic search value over the range 1 max of piles. The key insight is converting a minimized value under constraints problem into a searchable space by thinking of k as the answer and checking feasibility using the simulation. This type of problem is called binary search on answer, okay? This type of problems are called binary search on answers, in which you figure out the range from the answer, right? Okay, so I hope you understood the intuition explanation. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. Let's start by handling the edge cases. If the pile's length is 1, Koko it just eats the pile fully, okay? That's all. That's the thing. If there is only one value, that is the answer, right? What we do, we just divide. Suppose if it is 6, okay, so we divide it by the maximum value, which is h, and we get something. That is our answer. Because with only one pile, Koko must eat it in h hours, right? We divide the pile size by h and round up it. Always remember, h value will always be greater than or equal to the length of the piles and 10 to the power 9 as per the constraints, right? So at least h value has to be equal to the length. So suppose if pile's length is 1 and the value of, then h has to be 1. H has to be 1, okay? And suppose pile's value is 3. So 3 divided by 1 is, so it will give 3, okay? So they're gonna eat 3 bananas per hour so that they could complete within the h hour, okay? Now step 2, we initialize binary search after this edge case. Low will be 1 as I explained earlier. A max will be the piles max of the piles, okay? If C eats faster than the target pile, it is unnecessary. Any speed above max pile is redundant. So this is what I explained earlier in my easy language, okay? Now step 3, we perform the binary search. While low is less than high, while low is less than or equals to high, simple binary template, we calculate the mid value, low plus whatever I have written in here, low plus high minus low divided by 2. We calculate the total hours required at a speed mid, okay? So what we do, as if you remember, we create a function calculator, calculate hours, something like that. We created a function, right? Calculate total hours. So what will happen? It will be total hours, okay? Let it be HR, and calculate total hour, okay? Total hour. I'm writing in short form. We send here piles and the mid value, and this function will loop through the complete piles array, and piles of I will be divided by the mid value, okay? We'll sum this complete value and we will return from here and store it in the total hour, and then we will check here if it is less than the given h, that means the speed is valid, but maybe we can do better, right? Therefore what we do high equals to mid minus 1, okay? That means that we try to reduce the denominator. Else if the value is greater than h, that means we have to increase the denominator. Therefore what we do mid plus 1. The speed is too slow, Koko takes too long, okay? Now step 4, we return the final answer. After completing the binary search, what we do? We just return the low, because at the end, low will be pointing to that particular value or the midpoint, which is our k. Okay, we always string towards the minimum k that satisfies total hours less than or equals to h. When high is less than low, the smallest feasible speed remains in low. Okay, so I hope you understood the approach explanation. Let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So if you could see here, we have defined parameters for binary search. Low equals to 1, max value from the piles, and if the length of the piles is 1, we just return the seal value dividing that value by h. Okay, and after that, this is the edge case. After that, what we do binary search. We take out the mid value. We call this function passing the piles here and the mid value here, which will become k basically. Okay, instead of h, you could write it as k also, no matter what. So you iterate to the piles array and you divide each pile by h and you sum it up, and it should be a seal value, and we return total at the end. Now this function returns the total hours, and if we check it, if the total hours is less than the given h, that means we have to, that is the possible answer, but we have to check with lesser denominator value so that there might be a chance which is equal to the h. That is why we reduce the search space from the right hand side and come back to the left hand side, or you could say we throw down the right hand side of the search space. Else, if the total hours value is greater than the h, which means that we need a greater denominator, that is why we increment the low by doing mid plus 1. And after completing all this thing, we return low at the end. Now time complexity for this code becomes n log m. Why? N is the time taken by this particular pile to iterate, and log m is time taken by the binary search. Okay, simple as that. And space complexity is O of 1 because we are not using any extra data structure to store the answer. We are just using constant variables. That is why space complexity is O of 1. So I hope you understood the core explanation. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. For understanding, I have brought down the code here. So let's do the dry run for this particular problem. Okay. So low is 1. Okay. Let me write it somewhere. Okay. L. Okay. Wait. Let me draw the structure by that line also. So since there was not a lot of space here, so I have just written it till you could say 21 and dot 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 to 30. Okay. We'll figure that out. Let's start. So low is 1. It's standing at 1. High is max of piles. So high is standing at 30. Okay. So now what will happen? If length of piles is equals to 1, which is not the case here, so this will be nullified. While low is less than equals to high, we will take out the mid value. What is mid value here? Low is 1 plus high is 30 minus 1 divided by 2. Okay. So 29 divided by 2 is 15 or 14 plus 1. Okay. So it's 15. Okay. Mid value is 15. So we write 15 here. And after that, what we will do? We will call this function. Piles will be passed here and mid 15 will be passed here. So what we will do? We'll come back to this function. Total is 0. Now we divide piles each value by 15. Okay. So this, so we'll just directly write here. Okay. Let me do. So 30 divided by 15 is 2. This will be 1. This will be 2. This will be 1. And this will be 2. Correct. So 2 plus 1 3. 3 plus 2 5. 5 plus 1 6. 6 plus 2 8. Okay. So we got 8. So we return 8 from the total. Now we have total hours equals to 8 now. Okay. Is 8 less than or equals to h? No, it is not. It is greater than h, which is 6 here. So what we'll do? Low equals to mid plus 1. So this mid L will come to 16. Great. So again, we will calculate the mid value. Okay. So if we'll calculate the mid value, it will be 16 plus 30 minus 16 divided by 2. So 30 minus 16 divided by 2 plus 16 gives me 23. Correct? So we pass this 23 here again and piles value also again. So 30 divided by 23 is 2. This is 1. 23 divided by 23 is 1. This will be 1. And 20 divided by 23 is also 1. So if we add it up, it is 4 plus 2, 6. So total hours is 6 right now. And it is equals to the h. So what you do? You do high equals to mid minus 1. Okay. So what will happen? Mid value was how much? 23, right? Mid minus 1 will be how much? 22, right? So h will come to 22. Let me draw the number line properly now. So our range is now 22. Okay. So h is standing here. Again, we will calculate this particular value, 16 low plus high, whatever it is. So if we do that, 16 plus 22 minus 16 divided by 2 gives me how much? 22 minus 16 divided by 2 plus 16 gives me 19. Okay, so mid value is 19 now. So again, it will go back to this array and we will divide it. The same thing again. So 19 will take to divide this 2 hours, 1 hour, 2 hour, 1 hour, and 2 hour. 2 plus 2, 4, 5, 6, 7, 8. It is greater than h. Okay, if it is greater than h, what will happen? It will happen mid plus 1. Simple as that. So mid was 19, so L will come to 20. Got it? This was 8. Okay, 9. Again, we will calculate the values. So 20 plus 22 minus 20 divided by 2. So it will be, I guess, 21. Okay, now we will pass 21 again here. If we divide 30 by 21, it will take 2 hours. 11, 1 hour. 23 will take 2 hours again. 4 will take 1 hour again. 20 will take 2 hours again. Again, the value becomes 9, right? That means low will increase again. So now it is 22. Now L is standing here. Okay, let's calculate the mid again. It is 22 plus 22 minus 22 divided by 2 gives 22, right? Then we pass this function here again. Again, we will come back. It will take 2 hours to divide 30, 1 hour for 11. 23, it will take 2 hours, same. 4, 1 hour. 20 also 2 hour. Again, it sums up to 2 plus 2, 4, 5, 6, 7, 8. Sorry, it was 8. Earlier also it was 8, not 9. Okay, 8. So again, 8 is greater than this value. So what will happen? Low will become mid plus 1. So now low value is 23. Okay. When we go back, what we see? We see that low has already crossed high. So this condition becomes falsify and we return the low, which is 23. And you could see the output for this particular problem is 23. So I hope you understood the dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, the code, and also the binary search concept if you don't know. After that, do a dry run by yourself for 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. So, so I will start by writing the calculate function first. Okay, def calc. I will just write calc. Okay, self files, and I will write k here. Okay, total equals to 0 for pile in piles. Total plus seal value of pile divided by k, and at the end we return total from here. Simple. Now in the main function, I will declare low equals to 1, high equals to max of the piles value. Then if length of piles equals to 1, we just return piles of 0 divided by h. Okay, there also seal value. Otherwise, while low is less than equals to high, we calculate the mid, which is basically low plus high minus low divided by 2. Now what we do, we take a total hour. Okay, equals to self dot, we call the calculate function here, pass the piles and the mid value. Now if total hours is less than or equals to h, that means there are possibility that we should reduce the search space from right hand side. So we do mid minus 1, else low equals to mid plus 1. Okay, and at the end we return low. Let's try submitting the sample test cases first. Okay, so there was a spelling mistake here. Let's try again. Now let's submit the complete test cases. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.